In case we haven't met before, I'm Jonathan Lee Martin, aka Nibbler on the web. I'm a web educator, an author, and international speaker. My passion is to help other developers craft their best work, achieve personal and professional goals, and grow without bounds. My favorite way to do that is by training others to craft exceptional software, usually JavaScript. Sometimes you can pull me off track of JavaScript, but I do love my JavaScript. And I do that through speaking, writing, workshops, and then through a YouTube channel called TLDR. It's a Codecast series targeted at working web developers. So I've worked with a lot of developers at a bunch of different skill levels. If you happen to be looking for training in your team, maybe some cross-training, if you want to help some intermediate developers level up to advanced, or you're just trying to cross-train a team that doesn't have any experience coding, I would love the opportunity to work with your team, whether that's an immersive 5-day boot camp halfway around the globe or right here in Charlottesville. I would love the opportunity to get to work with you. So afterwards, if any of that sounds interesting, or if I have to do a better sell and sound more salesy, then just tag me afterwards or head to jonathanleemartin.com. So before we hop in, I'll just give you guys a really quick roadmap of some of the topics that we're going to walk through today. We're going to start off by motivating the problems that lead to distributed editing in the first place. And we're going to walk through one of the first paradigms for dealing with conflicts, and that's called operational transformations. You've probably heard of them before. And then as we go a little bit deeper, we're going to introduce some terminology to help us talk about some of the trade-offs and some of the drawbacks we run into with something like operational transformations. And we're going to use that kind of as a springboard into a completely different paradigm for solving these kinds of problems called CRDTs. And then we're also going to take a look at some of the bleeding edge developments. There's actually been a lot that's happened in academia and the industry, even just in the last few years since I first started looking into this and gave a talk, a lot of the slides based on that talk. And so much has changed since then, even in the academic world. There's like 5 new papers on all these cool new things. If by some miracle there is any time left, there will be Q&A, but Michael's looking at me and he's like, that's not going to happen. He knows this. He knows this all too well. So a little bit about the motivation behind this. Most of my life is spent waiting for NPM install to finish. So while it's running, I spend my time trekking around the world as a fine art landscape photographer. And failing that, I just try all the coffee shops I can find in the cities. So that's pretty much my life. And that lifestyle has allowed me to invest in landscape photography. Now, people who live on the go like this, working from wherever, are typically called digital nomads or location independent, kind of whatever seems to be the most popular term at the moment. And it's not just photographers who live nomadically like this. Digital nomads come from a lot of different professions. They might be bloggers, they might be journalists, developers. So a lot of different backgrounds, but they tend to have a few things in common. And that is that they're often trying to collaborate with other colleagues on the go, including places with really poor Wi-Fi, really poor internet, or no connectivity at all. So pretty much for a digital nomad, this is what our Wi-Fi connection looks like most of the time, because we'll be in a hotel or McDonald's. Those are probably our 2 best bets for internet connectivity. So digital nomads, because of this poor connectivity or sometimes no connectivity, while being in an occupation that has them be highly collaborative, they face a lot of interesting challenges that aren't always solved by a lot of the mainstream tools and applications that we would otherwise recommend to these kinds of people. So we're going to imagine 2 hypothetical travelers with these awesome GitHub avatars. This is Alex and Beth. Alex is a foodie, a hypothetical foodie, who is interested in food culture and trying cuisine from all over the world. And Beth is a travel journalist. So we're going to take these 2 hypothetical travelers, just because one's name begins with the letter A and the other begins with the letter B, and it's a whole lot better than, oh, I'm trying to remember what in math they usually use for the letter A. Thank you, Alice and Bob. I really didn't want to do Alice and Bob, so I did Alex, Beth, and Charlie, I think. So we're going to go with Alex and Beth instead, and these are going to be our 2 hypothetical travelers. So Alex and Beth are traveling through Europe together, and they're writing a blog post about sandwiches. They want to create this really amazing expose on sandwich making. So for the art of sandwich making, what sorts of tools would we recommend to writers, to travel writers in particular, like Alex and Beth? So that's a question for us as developers. What would we recommend to them? Especially since as developers, we might know of tools like this. We might know of Git, and that's great. It works great. You could be anywhere in the world. You could be working on some code, and hopefully at some point you can get an internet connection and push up your code. If there's any conflicts, you go through the pull request workflow. So as developers, we might like something like Git because it's offline first. It assumes that you're not online when you make these changes, and it has some very advanced workflows for merging those changes, because we don't want those to just be automatically merged a lot of times, because we know that you can have changes that actually merge but do not produce a correct program, even though it may appear semantically correct. Well, what about for writers then? Well, it's not exactly that well suited to writers. I've tried to sell a few writers actually on Git before, and this was the first impediment. Well, then I showed them a GUI. It still didn't get me very far. So most writers not really going to go for something like this. The interface isn't exactly that memorable, and on top of that, it's definitely not real time. So I can see it now. I'm working on a document with Michael back there, and git commit push. He does a git commit push for like 1 character changes. It's not real time. So what would writers reach for? As developers, we know what we might reach for, but what would a writer reach for if they want to collaborate with another writer? They would probably go for something like Google Docs. Now, Google Docs is really cool. It is real-time. It works great when you have a full-on internet connection. It even works okay when you go offline for a bit and get back on. And there's even an offline version of Google Docs. The problem is, if you do lose your internet connection, even if you have an offline version of Google Docs installed on your machine, when you get back online, if you've been off for long enough, the way that it merges those changes is not going to be that great. And on top of that, why should you have to be connected to Google? What if Alex and Beth are on top of a mountain somewhere in the Alps without any internet connection? They're side by side, okay? We've got 2 computers that definitely have all these incredible wireless capabilities. Why can't they collaborate? It's not because of connectivity. It's because they need a single source of truth. They need to be able to connect to Google Docs servers. So that can be a limitation for writers in some really hardcore conditions. So if we want to help our hypothetical writer duo collaborate from anywhere, like the top of a mountain or an isolated village, we need to figure out something that works in a more peer-to-peer fashion. Now, there's a lot of different pieces that go into creating a compelling collaborative experience for digital nomads. We're just going to focus on the algorithms that power the collaborative algorithms. There's all kinds of amazing peer-to-peer networking stuff out there. Your phone even is on Android. It's got Wi-Fi Direct, LTE Direct. There's all kinds of really cool technologies for enabling the connectivity, but we're going to deal at the level of data. How do we write editors that expect conflicting simultaneous changes to happen at the same time? And how do we figure out how to write something that can solve those conflicts? So that's the layer we're going to be focusing on. We're not going to worry so much about the peer-to-peer network or the topography or even like really cool editors and things you can do. We're just going to focus on the conflict resolution algorithm. So the basic question we're wanting to answer is, how do we resolve conflicts when several people are editing the same document, whether that's a Google document or some sort of written document, or maybe it's even sheet music, or maybe it's a Redux store, or maybe it's a bunch of to-do lists, maybe it's a grocery list or something like that. How do we allow multiple people to edit those data structures simultaneously? The first thing we have to take for granted is that we have a fundamental limit, and that is the speed of light is slow. Or at least it takes a non-negligible amount of time to fire off a packet through the internet of pipes. So if we just take that for granted, we take it for granted that if Michael and I are working on a Google Doc and we're typing characters, if we just assume that when I type a character, it might take a split second to show up on his machine, and meanwhile he could have typed something, if we take that for granted, that's where these algorithms are going to help us out. And then we don't have to worry about how long it takes. Maybe if Michael decides to go offline for a bit, and then he comes back online a few seconds later, or maybe 2 days later, the same sorts of algorithms should be able to help us out. So for Alex and Beth to be able to make changes at the same time, we need some sort of algorithm that can merge those changes. Moreover, we want to merge those changes without supervision. So unlike doing say a git commit or a pull request where you know that you're probably going to have to go in and inspect the changes and make sure that it resolved them correctly, we want to come up with an algorithm that can merge them without that supervision. So that means that how those changes get merged has to be incredibly predictable, probably mathematically describable. I'll leave that to Mike. So that Alex and Beth will always end up with the same document. I think it's fair to say that's the one constraint we know no matter what we have to keep. If he and I are working on the same document, we both go offline and we make our separate changes and then we sync back up, we should both end up with the exact same copy of the document. So there's a name for this, and that's strong eventual consistency. Strong eventual consistency, it just means exactly that if we both have the same copy of the document to begin with, we go offline, we make changes, and then we exchange only the changes, we should both be able to arrive and derive the exact same final document. Now, eventual consistency is a relaxation of a different database paradigm, ACID. So strong eventual consistency is part of BASE. You probably seen that used as a really fancy acronym to get you excited about these distributed databases. They said it's a base database. Basically, the idea is rather than force everyone at any given point to have the exact same copy of the document, why don't we just require that at some point they arrive at the same copy? So for Alex and Beth, they probably won't have the same copy of the document if they're both offline and they've been making changes. So rather than locking them out from editing the document at all, we'll just require that once they get back online that they arrive at the same solution. So that's roughly what we want our algorithms to work like. So could we make an algorithm that satisfies eventual consistency? So let's imagine that Alex and Beth are hiking in the German Alps and they've decided they're going to have a picnic. They pass a market, so naturally they need to get some groceries. So they're going to make a grocery list and emoji, because why not? So this is the document they both start off with. So before they split and go their separate ways, they both have a grocery list. They both have copies of it. We might call these replicas in the distributed world. So here's the replica that they both have. They each have a list, a set rather. So order doesn't matter in this set. There are no duplicates. And they start off with a list that says we need milk, bread, and eggs. So they know this while they're online. And then they split and go their separate ways with no connectivity, and they make some changes. So let's imagine that they make these sorts of changes. Alex removes bread from the list, and he adds an apple to the list, whereas Beth removes milk. When they come back together, how do we resolve those differences? They both are going to have different lists, and strong eventual consistency says that they must both arrive at the same list now that they've exchanged their changes. So what sort of strategies could we have for resolving those conflicts? Well, right now the only requirement we have is strong eventual consistency. So here's a naive strategy. Let's combine both lists into a new one without duplicates. This would be the union strategy. And it is a valid strategy because Alex and Beth will both get the same grocery list, or in other words, union is eventually consistent. But there's another equally valid strategy, and that is we could use the intersection strategy to keep only the items that are common between both lists. This is also eventually consistent. So long as they relay the changes they made, they don't even have to relay their entire list. They'll arrive at the exact same copy of the grocery list. So both of these are correct according to strong eventual consistency, but neither really capture what we wanted. We wanted to capture the intent where Alex removed bread and added apples. Well, what happened to those changes? Neither strategy seemed to work. Let me step back through this. The first strategy seems to have basically just taken all the items, which means that we couldn't remove anything, whereas the second strategy wouldn't allow us to add anything. So that's a problem with the union and the intersection strategy, is they somehow seem to lose out on the user's intent. We could either pick a strategy where we can never add things, or we can pick a strategy where we can never remove things. Neither are great. So both of these algorithms are losing something in the user intention. So now, if we're going to make a good algorithm, we have to add this second additional criteria, and that is the algorithm must preserve the user's intention. It's kind of a hand-wavy idea, but we can at least say probably that this does not seem to capture the user's intention. What would be a better step? Well, what we could do is instead of doing a diff and relaying the diff, so to speak, what if we kept track of each operation that happens and relayed those changes? So Alex deleted bread and added apples. Beth deleted milk. What if we kept track of just those changes, and then when Alex and Beth both get online to sync, they exchange those changes? Well, then what we're doing is we could just union those change operations and then play them back. So if we play these change operations on both our copies of the document, we should end up with the exact same grocery list. And when we play that through, we arrive at eggs and apples. If you think through that, that does seem to preserve intention a little bit better. It allowed Alex to remove bread from the list and to remove apples, to insert apples, and it also allowed Beth to remove the milk from it, and we ended up with eggs and apples. So that's a decent strategy for working with unordered sets. Sets are pretty easy to solve. So we're going to try something harder now. Now that Alex and Beth have presumably finished their grocery shopping, they're ready to start working on that blog about sandwiches. It'll be some fantastic Wikipedia entry someday, but until then, this is the document they're both starting out with, just the word sandwich. Now this is not a set, and it's definitely not unordered. This is an ordered sequence, or we might just call it an array of characters. So if Alex and Beth both start off with this, and they go to make their changes, Alex might do something like deleting the letter D. I really missed a good opportunity here. I should have deleted the letter N, and then we'd have a sandwich. So Alex removes the letter D, Beth removes the letter H. Mind you, these changes happen while they are not connected to each other. So right now, when Beth goes to insert the letter H, she does not yet see the change that Alex has made. So this might work, but what happens when they sync up? Well, we could do the same strategy we were doing with the grocery list earlier. We could instead relay change operations. So Alex deleted the character at index 3. Beth inserted the letter H at index 5. So presumably, if we do that whole union strategy and relay changes between Alex and Beth, this should work. Well, except not quite. Instead of getting sandwich, which was the intention, Beth was trying to insert an H after the W and before the I. But no matter which way we play these operations, we're not going to arrive at something that makes sense. That's because when Beth inserted the letter H, the state of the document she was working on still had the D in it. But when her change actually gets played back to resolve those conflicts, it's now operating on a completely different state. So in other words, these operations are useless if they haven't been somehow transformed for the new state. Otherwise, we just end up with nonsense. So with that in mind, why don't we see if we could just somehow transform these change operations when we go to resolve the conflicts? So even though Alex and Beth made these changes concurrently, depending on whether we apply Alex's or Beth's first, we're going to end up with different solutions. So what if instead, so Alex and Beth have made these changes, they come back together. Now imagine we're trying to play these operations one after another to catch up. Again, they have to arrive at the same copy of the document. Well, what we could do is we could arbitrarily decide that all of Alex's edits, if Alex and Beth edited something concurrently, we could say that Alex's changes get played first and Beth's changes will get played second. So with that in mind, what if we first played all of Alex's changes, because we know that those are based on the current state and that those operations should work. So we'll play that first. But then we'll keep track of how it changed the state of the document. In this case, it shifted all of the indices after D over to the left. So it shifted the index by -1. Now when we go to play all of Beth's operations, we're going to transform all of her operations by that index if the insertion comes after the change point. So now instead of doing an insertion at 5, we'll do it at 4. And we arrive at sandwich. So this preserves user intention and is eventually consistent. So that, in a nutshell, is operational transformations. A lot more edge cases to think through, a lot more complexity around operational transformations, but that's the basic idea. So when changes are made concurrently, each client performs the change in some agreed upon order, a well-defined order. That might be alphabetically, like maybe you play all the changes by Alex first because his name starts with the letter A, and then Beth's changes second. So long as you transform all of Beth's operations in terms of Alex's, you should arrive at something that makes sense. Now, for operational transformations to work, they have to satisfy two mathematical properties. They're just called TP1 and TP2. A lot of crazy math that I can't read. I prefer pictures. So if we have two documents, if we have the same document and Alex and Beth make changes, and then they relay just the changes, strong eventual consistency says that they must both end up with the same document. So here's an example of our earlier flawed algorithm, whereby when we relayed the changes, we actually arrived at different copies of the document. So that's the first problem that a good operational transformation has to solve. If it runs into this issue, it is not eventually consistent for what we need. So that's TP1. TP2 is a lot harder. TP2 says, now we have Chris. I'm sorry, it wasn't Charlie, it was Chris. TP2 says if 3 people are editing something at the same point, so imagine that Alex and Chris are trying to insert a letter near the middle, but Beth deletes the letter that was in the middle. That was sort of the reference point. How do we get all 3 of them to arrive at the same copy of the document? Will they arrive at AXYC or AYXC? So that's called TP2. So if an operational transformation obeys and fixes both of these problems, TP1 and TP2, then it can be used for multi-peer editing. Before, with Alex and Beth, it was just 2 people. If you want more peers than that, it needs to satisfy TP2. That means that all copies of the document will be eventually consistent once we relayed all the changes between peers. The trouble is that for text documents, there aren't really any correct transformation functions out there. That's actually a little bit of a lie. There's been a lot of really good research in that space because operational transformations are, to date, probably the most popular version of doing any sort of this collaboration stuff. They're just insanely complex to get right. At the time that this particular paper was written, though, there weren't any correct implementations of operational transformations that satisfy these 2 properties. Basically, what it means is you can't have more than 2 peers. It's fine if you've got 2 people, but if you want more, you can't do it. So how does Google Docs work then? How can you have 5 or 20 people editing the same document? It's a cheat. So in Google Docs as one peer and someone who's writing acts as the secondary peer. And to that other peer, there's only one other peer, it's Google Docs. But Google Docs is now the source of truth, and Google Docs acts as the arbiter between all of the connected writers. So what this means is that you can't have a multi-peer edited document. They all have to connect to the same source of truth. So if you don't have a connection to Google, you're out of luck. Even if you've got 10 people all side by side with great networking capabilities, if you can't connect to google.com, you're out of luck. So this is how Google Docs works, and it is pretty amazing just how great they've made the experience. It just starts to break down when you start needing some of these more advanced offline capabilities. It also means that it's kind of slow. Now, Google Docs, it does feel fast enough for most of us, but if you were to watch it side by side or introduce a little network latency, you're going to see some delay because there's a lot of round tripping going back and forth. And you have to, if you want to make something like Google Docs, you have to have some servers like Google Docs if you want it to be fast like that. So Google Docs is not going to work so great when peers go offline for a long time. But it works. That said, could we move a little bit more towards a multi-peer type algorithm that does actually work with multiple peers? Are there some tricks we could do to solve TP2 compliance? So a couple different solutions, and these also are different strategies that'll pop up in some of the CRDT algorithms, is preconditions and tombstones. So let me show you guys a little bit of math notation. Mike knows this notation. Mike knows everything.
I don't know what you're talking about.
Nice. So this is called set notation. It's just a formal way to describe how things are ordered in a set. So this says that S must come before A, must come before N. So if you were to just split this out, this says that there are two relationships in here, that A must come after S and A must come before N. So that's all this notation means. So what we could do is we could take our document, and instead of writing it out as an array like this, we could write it out as this ordering that says that the S must come before A, must come before N, must come before D. You might ask, how does that work if you have a letter repeated in there? Well, what you would do is you would just assign a unique ID to each one of those letters to make them unique. So supposing you had this ordering, you might notice that this is it was a partially ordered set. This is actually a totally ordered set, which means that every element has exactly one thing it comes after. No, that's a lie. Each element has a very strong relation to all the other elements. There is no element in this list that you can't say what it comes before or what it comes after. That should be a question you can always answer. So in this ordering, instead, when we go to make changes, let's say we have 3 people making changes concurrently. We've got Chris, Alex, and Beth, and they make these 3 changes. Instead of them just telling each other which letter they're deleting, they're also going to encode some preconditions. They're going to say, by the way, when I delete that D, that is the D that comes before W and after N. And when Alex does his insertion operation, he says insert a Y and it should come after D but before W. Again, if there are duplicated letters in the sequence, just imagine these to be IDs. So when we relay these changes, we're basically inserting a little extra information to make sure that our changes between multiple peers don't get all muddled. Let's just say that we applied Chris's operation first. We deleted the letter D. The trouble is now the precondition of Alex's operation is not met anymore. We just deleted the letter D, which was referenced in his precondition. So we automatically can't apply Alex's simultaneous change. This brings us to the second concept, which is tombstones. So when Chris deleted the letter D, instead of actually removing it from our data structure, what we might do is we might just mark it. We might mark it as deleted, which we would call a tombstone. So it still takes memory, but we can at least mark it and say, hey, this isn't actually here when a user is looking at it or to the person editing the document, but we're going to keep track of it. We're going to hold on to this history. So if we did that instead, now when we go to finish applying these operations, we can see that Alex's change of inserting a Y, well, yeah, there's no D there now, but there used to be, and we can see exactly where it used to be. So now we can apply that operation. And then we can go ahead and apply that. Now, it's important to note there's no reason that Alex and Beth's operations had to be applied in that order. So if I were to go back and play those changes, you'll notice that the E could actually come after the Y instead of before. So when designing these algorithms, you have to come up with a well-defined order that will always break ties. Right now, we don't really have a tiebreaker in here that says, should the E come after the Y, which was concurrently inserted, or before? Those are important questions for an algorithm to answer. But at least by using preconditions and tombstones, we were able to put together all of these simultaneous changes and arrive at a document. So tombstones and preconditions are a common trick in a lot of different algorithms, not just operational transformations and not just in 1 or 2 CRDTs. They just allow multiple peers to collaborate on the same document without a central server. The trouble with tombstones is that they take memory. So if you have a document that's been edited a lot, you might have just a few characters in it that takes several megabytes of space because all of those tombstones are still there. So, well, if you've got all of those tombstones there, can't you get rid of them at some point? You can. You have to basically invent a garbage collection protocol, which is expensive and time-consuming. And it means that Alex, Beth, and Chris must all be online. suppose that Alex has a bunch of changes that he hasn't yet relayed to Beth and Chris. Well, then Beth and Chris can't go deleting all their tombstones. They have to wait until all of the peers are online, and they can essentially do a big garbage dump all at the same time. That's very difficult to arrange and to code up. It's very feasible, and there are implementations out there which do it. It's just a royal pain, especially when we were trying to get away from this whole idea of everyone has to be online for this to work out. So this brings us to a different paradigm of ways of dealing with conflicts. So CRDTs are a class of data types, like a linked list, an array, or a tree. They're a class of data types which seemingly resolve conflicts without any special transformation algorithm. So there's a lot of different CRDTs out there. Now, data types and algorithms, pretty much interchangeable, but sometimes data types are much more elegant to think about. Or for me, it means I can actually whiteboard the data type, whereas the algorithm, not always so much. But CRDTs are a really cool area because they aim to be a class of data types that have conflict resolution baked in by not having any such thing as a conflict. So a few of the ones that are out there, they've been around for a while: sets, counters. If you've used React, if you've used, is it CouchDB or PouchDB? PouchDB, I can't keep them straight. There are so many distributed databases out there that already use a lot of the traditional CRDTs. However, while creating CRDTs for sets and counters and stuff like that are considered a solved problem, creating one for ordered sequences like text has taken a surprising amount of research, and it's actually still a heavily developed area to today. I think there was a new paper just like a year or so ago that I was looking through. So I've struggled through a lot of academic papers and implementations for at least 10 different algorithms, and there continue to be new papers published on yet another sequence CRDT. So today, out of all these different choices, because there's a lot of trade-offs, there's a lot of fall-throughs, a lot of these don't have good implementations. Dare I say, they don't have a JavaScript implementation either. So today, I want to focus on just my conceptual favorite, and I think this will help root us for quite a few of these that all kind of have at least a fair portion of them have kind of the same strategy and the key insight, and that is LSEQ, the linear sequence. So unlike a lot of the other ordered sequence CRDTs, LSEQ is going to be fast and memory efficient. Remember, the trouble with the tombstone idea with operational transformations is we have to keep track of tombstones, or else we have to do a big garbage dump at the same time. With LSEQ, the idea is, couldn't we write a data structure where tombstones just seem to drop off when they're not referenced anymore, and we don't have to sync up to remove all these tombstones? Better yet, could we maybe not have to think at that level since it's a data structure? That's kind of the idea of LSEQ. Now, there's a lot of different ways that we could represent a string in memory on computer. The easiest would be an array of characters, but a lot of programs use some sort of tree structure to store data. So like a binary tree. Tree structures have a lot of great properties in regards to performance and memory usage. So LSEQ is based on a representation of an array that is like a tree. So in the LSEQ CRDT data structure, we have a special kind of exponential tree. This tree will have a root node that can have, in our example, up to 10 branches. You can configure that factor. Each branch is going to be labeled from 0 to 9. The first branch of each level and the last branch of each level are reserved. But all of the other numbers can be used. I'm just realizing that I think I broke that rule actually in this, so we will find out. So each branch is going to be labeled from 0 to 9, and at each level and at each node, you get to use up through 0 through 9. Each subtree will work that way as well. So if you wanted to read out what this tree represents, to convert this tree to a string, we just visit the nodes with a depth-first traversal starting from the left. So if we do depth first from left to right, we go down and we hit S, A, N, D, W, I, C, H. So that's kind of how we read out what this tree represents. Now it's important to point out, there's already now in our brain two representations of the string we're working on. There's the actual string that we expect to see on the screen, and there's also the tree, which is sort of like the model. So this is one of the more confusing parts of a CRDT, is this idea that you have a view and you have a model. You have the model, which is the tree, which is memory efficient, it's performant, but then you have the view, which is how a user will actually interact with it. That is a difference that doesn't really exist in operational transformations, and unfortunately, that is a common place for performance issues to hide, is in this difference between the view and the model layer. In fact, once we get through LSEQ, you might think it's just 1,000% the best thing ever. It is still 1,000% the best thing ever, but it's actually got some performance issues because of this hidden difference between your model and your view. Now this tree has 3 levels. So to specify any particular node in the tree, basically its address, I could point out the particular branches that you would take to get to that node. So if I wanted to address the letter D down there, we would see that the address is 377. And that's like a unique address that that particular node gets. So whenever a user is going to make a change to the text document, we could reference that particular node with this special ID. So to make a change, we could create an operation that uses those IDs. If we wanted to insert the letter Y between D and W, we would just relay those special IDs, and the result of the insert operation is going to be 2 things. It's going to insert that node, but it's also going to allocate for us a brand new ID. So it will give us a brand new ID of 3.7.9. So if you read through that, 3.7.9 kind of looks like it's between 3.7.7 and 3.8. So that's the new ID that this node is going to have. Now to apply that change to the tree, we'll just start stepping through the tree and we'll add it to the corresponding node. Now if this is Alex's copy, Alex is the one who did this insert operation in the first place, so we know there's not going to be any conflicts, because he's the one that made the change and he made it based on his copy of the document. But what about Beth? What happens when both of them are making changes and they haven't yet relayed those changes? Will this tree structure deal with that problem? So let's say that Beth inserts the letter H at 3.8.2. Well, let's say that we just play both changes. Maybe we don't, let's just not worry about trying to transform these operations. Let's just play them forward and see what happens. We play Alex's change. So far, so good. We play Beth's change. So far, so good. When we read it out, we get Sandy Witch. So this is kind of the illusion that CRDTs create. There was no conflict resolution algorithm because you can't have a conflict. There's no such thing as a conflict. Seems a little bit like a lie, and it sort of is, but it's a really beautiful lie. So with CRDTs, conflict resolution seems to be baked into the data type semantics itself. Now, as I said, there's a little bit of hand-waviness there. Now, first off, this algorithm is as beautiful as it seems, can say that. But there are still some difficulties we have to face. For example, when we allocated that ID of 3.7.9, who was to say that it had to be 3.7.9? We actually had more than one choice between 3.7.7 and 3.8. We could have done 3.7.8 or 3.7.9. So why did we pick one over the other? And will those IDs ever be reused? So this is the first thing to consider. These IDs must be immutable and unique. Immutable and unique. If either one of those properties is not the case, none of this algorithm works. So in LSEQ, we have to guarantee that these IDs have both of those properties, so they should never be reused and they should never be changed. So that means that as we edit the document, if IDs are never going to be reused, something's got to grow. It's almost like having tombstones without having tombstones. So that may not seem like a big deal, but every time you need to insert a letter between 2 IDs that have no gap, like 3.7.8 and 3.7.9, if you wanted to insert a letter between those, you now have to drop down an additional level. Every time you add a level to this tree is a chance for it to be a little bit more imbalanced and to start losing out on some of the performance details. Moreover, as that ID gets longer, it takes more bits to relay that ID. Now in practice, that's not a big deal because with the LSEQ tree, those IDs actually can incorporate more nodes at every level, which means that it gets deep very, very slowly. So in practice, that doesn't end up being a big deal, but it is important to consider because some algorithms, some CRDTs, are built around the idea that these IDs don't get longer and longer without bounds. They usually put a bound on it. But if we weren't good about picking our IDs as we went, we might end up with a tree that looks like this, where it essentially becomes a linked list. And the performance actually becomes worse than linear because the algorithm is expecting it to be shaped like a tree. So if you don't pick those IDs well as the user is editing the document, you're going to end up with something that gets none of the performance benefits. In fact, it's going to be penalized. So the LSEQ paper actually centered on how to pick a good ID. That's actually the paper spends about 3 or 4 pages talking about the data structure we just saw, which is called the Logoot tree. I think it was the best explanation I'd seen, actually, so I thought the paper was all about that. Actually, their paper is all about how do you pick a good ID, which is a subtle but very, very important question to ask. But overall, even though it's got some drawbacks like that, LSEQ is very powerful for text documents, and unlike operational transformations, it does not require a central server. So we don't need to all connect to Google to make changes. So long as we have some way to all connect to each other through networking, we can just relay changes directly to each other and all arrive at the same copy of the document. This algorithm also doesn't explicitly rely on tombstones or complex garbage collection strategies. Those are just additional details that you as a developer of these algorithms have to get right. So that is one of the big appeals of CRDTs, is that by having a strong conceptual model, you may be able to describe these tests better in terms of a data structure and write a nice test suite. So there's something very intellectually satisfying about it. So no tombstones, no complex garbage collection strategies. Because those IDs are immutable and unique, deleted nodes will naturally disappear from the tree when they are no longer needed. Now, in turn, that means that the size of an LSEQ structure grows slowly. So let's say that you insert 1,000 characters and then delete 1,000 of them. The size of the LSEQ tree is probably not going to be 0, but it's going to be a lot smaller. So it does tend to deal better with monstrous amounts of insertions and then followed by deletions. That's important because that means when we apply operations in the future, it should be decently fast. Again, it's not perfect. At a cursory glance, you might think all of these operations are generally going to have a big O of log n time because of that tree structure. But there's actually a hidden performance penalty that I mentioned, and that is when we convert from the view to the model or vice versa. So let's imagine this. I, as Alex, want to insert the letter H at the index 4. What ID in the tree is represented by index 4? That's a question we have to answer. To answer that question, we have to actually search through the tree and keep track of a few extra properties to find it. And it turns out it kind of breaks our log n time that we expect from just having this tree structure. So that can be a little bit challenging. And in fact, some of the follow-up algorithms, or CRDTs, try to solve that problem because it's a very common issue. So in other words, there are some performance costs hidden in any translation from view to model coordinates, and that will need to happen every single time you insert a character or remove one. Because each character is its own node, you can't really batch up changes either. So if Michael inserts 2 paragraphs of changes, sure, over the network, he could just relay that he inserted, gosh, actually, even that's hard to do. He would have to relay to me each letter along with its new ID in the tree. Now, you could come up with ways to try to sidestep that, so maybe you don't have to tell me all of the IDs and maybe I can somehow intuit them, which is very challenging. But still, you're going to end up having to insert every single node into the tree, even if it was just a paragraph. That can be problematic when people go offline for a long time and they've inserted a page full of changes. So if furthermore, if 2 editors are inserting a word in the same spot. So Alex and Beth were working on sandwich. They go offline and they both add different things. Maybe one adds are awesome. The other adds are delicious. Kind of seems like when it syncs back up, it should come out as sandwiches are awesome, are delicious. Or maybe reverse the 2. No, actually. With LSEQ, it will interleave those characters in a seemingly random order. So again, we seem to not be getting user intention with this. So that's a very big problem if you go offline for a while. It doesn't tend to be as much of an issue when your peers are online, because if I start typing the phrase "are awesome," Michael hops in and he starts typing "are delicious," I will probably see that he's making the change and stop making mine. So it really only becomes a problem in certain extreme cases. All right, that was a lot of time in the conceptual space. So what should you try out today in your JavaScript code base? A couple years ago, I would have told you I haven't the slightest idea. There was no JavaScript code that I could find out there. Over the last few years, there has been some amazing implementations of some of these algorithms. So in particular, the LSEQ data structure has some flaws, but there are about 3 follow-up algorithms, CRDTs, that make some really cool improvements to them. One is called the dotted Logoot split AVL tree. Way too many terms. Basically what it means is that it can deal with the interleaving problem. The IDs grow more slowly, and it just tends to be much more memory efficient. So that's pretty cool. That, to date, is my favorite implementation. I did a short link there. That's j.mp/logoot-split. That, to date, is my favorite implementation. That's a really cool library, but maybe you say, well, I want to sync a Redux store. I'm not going to represent that as a string. Well, that's where AutoMerge comes in. AutoMerge is a library by Martin Kleppmann. Martin Kleppmann put together this amazing paper, actually about a month before I first gave this talk a few years ago. And it's an algorithm for a JSON CRDT. So if you can describe that document as a JSON type structure with arrays, with nested objects, with numbers, other scalars like that, if you can represent it that way, AutoMerge can resolve conflicts and track those changes between it. It's pretty awesome. Martin Kleppmann wrote some amazing JavaScript, which is really surprising was really surprising to me coming from academia. I'd been reading all this awful source code. Martin Kleppmann wrote an exceptional library. It is actively maintained. Highly recommend. So basically, if you want to sync a part of your Redux store over peer-to-peer, you've got to do the networking layer, but at least this will handle the algorithmic side for you. So this is probably what has me most excited. I only discovered this a few months ago. I got all excited because when I first saw the paper, I read through it and tried to implement it myself and hated my life. Didn't get very far. I also tried to learn Scala and Haskell so I could read some other people's implementations. It didn't go well. So highly recommend you check out AutoMerge. He has some great demos where he has an application like Trello, and there's no central server. You can have as many peers as you want, and once they're connected up, they're just editing a Trello board. And it has strong eventual consistency. It preserves user intention. It even deals with changes to strings that are nested within your JSON payload. Now, one important thing I'll point out with AutoMerge is that it can treat strings like a list, and so it has its own resolution algorithm for when 2 people make changes to an ordered list, but it's not Logoot, it's not LSEQ, it's an algorithm called RGA-split, which uses tombstones. So if you're making something like Google Docs, and these are long, long, long documents, and users are making tons of changes to them, RGA-split, which is what he uses for the string algorithm, is not going to work so well in terms of memory. But if that's not the case, like you've just got Trello cards and you've got 2 people collaborating on these descriptions, which are probably under a kilobyte, not going to be an issue at all. It's just if you have text that gets edited over and over again, like a Wikipedia entry, you're not going to want to use the particular algorithm, at least I don't think, that he uses. That said, he's a really smart guy. He knows what he's doing, and he's made some really cool trade-offs. He actually wrote some of his own research on RGA, which is one of the other algorithms, to try to make it work better just for his own algorithm. So Martin Kleppmann's really awesome. And he's really nice on GitHub too. So if any of this interests you, seriously, go hop into AutoMerge, ask him a question. Don't say I sent you. He might be irritated, but he's a really cool guy. All of that just so we can help these 2 people, these digital nomads. Well, we focus on collaborating as a writer, but I want you to think about this and be a little bit more inspired to think outside of writing and think in terms of, say, editing music, maybe editing sheet music, MIDI, maybe editing drawings, maybe editing a design board or a mood board. Basically, these algorithms don't have to apply just to string or text or whatever. Pretty much anything you can represent as an ordered list or as a JSON structure. These are the sorts of things that will enable you to create lots of really amazing collaborative experiences for folks on the digital nomad lifestyle. Final plug, that is, if you have any training needs, please get in touch, because Charlottesville is awesome. But also, if you happen to have folks not in Charlottesville, that works well. Michael, how are we doing on Q&A?
Oh, we got a little time for Q&A.
Dude, questions?
Okay, I'll go. So, I didn't totally understand you're saying there's no tombstones, and we didn't actually like walk through a deletion operation, so I might just be like not picturing it correctly. But I mean, you can't, like, if you delete the S here, do you rebalance the whole tree right then? Or do you wait until later, which sounds a lot like tombstones?
This algorithm has no rebalancing. Because you're right, if you rebalance, that means reallocating IDs or changing the structure of the tree at least, and that has to be done in sync. So no, LSEQ puts all of the cleverness on figuring out a good ID up front, so that way, even though the tree is going to have some imbalance, you can at least prove that even for adverse editing behavior, that it's going to stay roughly balanced.
So what happens to the S in this case if he deletes it?
So if you were to delete the S, because that one has subnodes under it in both people's copy, it won't go away. It'll be marked. So in a way, it is a tombstone. Now the memory for the S will go away, but come on, that's one character. The node will still be there, but that's because it's referenced on Alex's copy. You won't have to keep track of someone else's tombstones if you don't have something that's underneath of it. So let's say for a moment that both Alex and Beth were to delete the subtree under S, and they both did that, the S will automatically disappear. So yes, there is still, and this is where CRDTs can sometimes be a little bit kind of clever, is that they hide some things that sound eerily like tombstones and preconditions. And they sort of do. But the nice thing is we don't actually have to come up with a strategy for doing the garbage collection. That's the more important part here with tombstones. It isn't so much that we don't have them, because we sort of do. The more important part is, did we have to come up with a protocol where all of the peers get online and now collaboratively get rid of all those tombstones?
So I guess I'm still having a hard time with it. So it's like, let's say I am deleting Sandy, like that whole part. But now I sync up with somebody and they're like, just kidding, I added a letter, in between the D and the Y. So there's some stuff down there. It seems like if I throw all those nodes away in the beginning and I see this new insertion, I kind of don't know what to do.
So what you'll do is you'll actually recreate those levels of the tree as you go, because the ID actually tells you.
Empty nodes, but that's okay.
Yeah, I guess the analogy that comes to mind is you used to have this big neighborhood and all of the houses were wiped out, but you have an address. And if the address literally tells you where that house used to be, you don't have to have all the other reference houses. You just have to have the address. So the only way that works, and the only reason it works, is because the IDs are immutable and unique. If you did not have both those properties, that would be the case.
And I guess since I'm peppered with annoying questions, that was the other thing. Like, if we are out of sync, what is the argument that we don't accidentally use the same ID for two different tasks?
Yes. So what the algorithm has to do is, instead of just having that, part of the ID is also the replica ID, which is basically, the replica is which user are you and which copy of our, basically each user gets a special ID and that becomes part of the ID, but at least that ID is small and does not change.
Yeah,
So that becomes part of it.
0 to 9 here, but this is really like,
Yes. And in fact, there's also two other parts to the ID that are omitted here. So in addition to the address in this tree, you have the replica ID, which is sometimes called the site ID. You have the counter, which keeps track, if I recall correctly, how many times an operation has been applied to that part of the subtree. and I think there's like some sort of causal vector or something in there. So there's quite a few parts to the ID.
So it's kind of interesting though. So like if we are likely to choose different nodes at the beginning, you'd think you wouldn't have this overlapping issue because I am going to pick a node to the left, you're going to pick a node to the right. We guarantee we're not going to pick the same node to start. I'm picturing this situation where you've both typed like a whole paragraph, right?
Well, that strategy ends up producing sort of like a linked list style thing. So you have to let each peer somehow select a random ID to prevent the tree from getting too tall. So there's certain elements of randomness where Alex and Beth are going to possibly have a conflict, but it's not that common. And in fact, the deeper the tree gets, in LSEQ, they actually double the number of nodes at each level. They did that, I think, if I recall correctly, to deal with a problem like that. So the likelihood of a collision just at that point, even with just the ID, gets less and less. But at the end of the day, there are additional pieces of information that resolve the tie, because for these algorithms to work, they must be able to resolve conflicts exactly the same way, which means there has to be a total ordering over all of the operations. There should be zero ambiguity. Yes?
It's interesting because our product actually deals with this problem or fails to deal with it in a very meaningful way. So the way that it's high level, the way it works is that you choose values from various form objects and it creates a text report from that selection. But we can have multiple users. What we've been doing is allowing synchronization of the data input elements, and that drives the creation of text. My question is, so for what I do, it's really critical that the result be consistent, but consistent correct. And if two people make a change, I want to be able to have both of them reconcile that change together. So does this algorithm, or are there ways in this algorithm that has a memory of the changes that I can then show the user, hey, you changed this, she changed this, let's decide together what the solution is for what they're in.
Two parts to that. So first, speaking to history, you could definitely track that. You could keep track of all of the change operations. As far as how you play that backwards, that you'd probably be on your own there. Like you could store snapshots of the tree for sure. There are actually a couple versions of the CRDT that work a little bit better with the history. But basically, you keep track of the operations. Now, as far as being concerned about when you resolve the conflicts, you might end up with something that is merged, but it's not semantically correct, kind of like merging source code. So to deal with that, normally the way you try to sidestep that problem is picking a representation of your data, like picking a database schema where creating inconsistencies is simply impossible in the specification. So for example, let's say that you've got this list, you've got this string and it's built up based on which things in a list you've checked. Rather than trying to do a conflict resolution on that string it produces, basically rather than doing conflict resolution on the view layer, you step to the model layer, which is a simple ordered array, and do the conflict resolution on that and allow the string to be a pure a pure view of that model. If even that isn't getting quite close enough, so a common example, if you're trying to edit a rich text document and you're trying to represent that as purely a string of HTML code and you try to do syncing with that, you can end up with strings of HTML that are completely unsemantic. So you don't. Instead, you find a representation that looks more, say, like a tree, like a JSON CRDT, and that then has fewer ways that you could create semantically incorrect resolutions. Even that, you probably still could create stuff that is semantically incorrect depending on how expressive your markdown language is. So at the end of the day, you try to sidestep as many problems as you can by picking a good representation, just the same as you would with the database schema. Honestly, if even your schema allows for inconsistencies or data that just doesn't make any sense, I'm honestly not sure. I feel like that can be a little bit of a one-off thing you've got to fix. Like maybe you could try to come up with a protocol for rejecting resolutions that are inconsistent, and you force all peers to pause and the user manually resolves it, kind of like you would with GitHub. But our goal at the end of the day was to prevent that sort of workflow. Yes.
Does the time when user A and user B made their edits factor into this algorithm at all?
Not in most of these, because if the time affected it, they'd have to have a central clock source. So the clock is only used to keep Alex's edits that he's made in order. So in other words, you don't even need a clock in that case. You have a simple counter. So long as Alex's edits are ordered relative to all his, and so long as Beth's operations are ordered relative to all of hers, it doesn't matter what time it happened at, and they don't have to know each other's clock. So it's only in terms of Alex's operations, those do have to come in a particular order. You might use the clock to keep track of that. More commonly, you'll just use a counter.
Is that counter across, like, I make some changes, I transmit them? Is that order just for that packet transmitted changes, or is it the total order for my entire interaction with this project?
The CRDTs generally don't speak too much to the networking layer, and so the counter is going to be in terms of how many nodes you've inserted into the tree as Alex. It's not going to be in terms of how you choose to transmit it. You might choose to package up a lot of these changes together and ship that off, like batching those changes. That's not going to be the counter you're going to want to use.
Any other questions? All right, sweet. Thank
Cool.
you very much.